So this is going to be a very interesting transition, I think. The next session is on changing knowledge in science, and perhaps that transition suggests that all the problems that we're talking about today requires us to consult both brain and heart and brain. So a little bit of contrast here. We've got two wonderful speakers to address the role of new science changing scientific methods in finding solutions to Western water problems. I am going to introduce both speakers, have them give their talks, and then we'll have a shared question and answer period. The first speaker is Dr. Alexandra Richey, who is a postdoctoral fellow in the Department of Civil and Environmental Engineering at Washington State University, to discuss techniques to monitor and manage groundwater using satellite imagery, really remarkable science that she's been working on. The second speaker is Dr. Jonathan Overpeck, Director of the Institute of the Environment, the Thomas Brown Distinguished Professor and Regents Professor of Geosciences at the University of Arizona, to discuss climate change, water, and the West. Please help me welcome Dr. Richey.
Thanks, everybody. I think it's kind of ironic that I'm following Kevin's talk because he showed so many beautiful visuals to help us understand on an emotional level as well as a brain level, let's say, what value we have in the Colorado River. Groundwater is a little bit harder to get people to care about on any level, emotional or otherwise. I also want to thank the Stegner Center for inviting me here. During my PhD in civil engineering, my advisor went to a 40th anniversary celebration of the Clean Water Act. And he came back and he just said, if you really want to make a difference in water, become a lawyer. So I don't think it has to be an either or, but it's nice to be here with a diverse audience. So I'm going to start off talking about what groundwater is, how we use it, just really taking it to the fundamentals of how groundwater moves and where it exists in our environment. And then talk about the ways that we measure groundwater, both the ways that we have historically and some opportunities that are underway now to understand larger scale groundwater systems. Let's start off just simply looking at where we have water in the world. The vast majority of water, as you guys know, I hope, is stored in oceans. Almost 97% of all water on Earth is in oceans. Salty, we don't want to drink it. That means that we only have about 3% of water on Earth that's fresh. And of that 3%, the vast majority, again, is stored away, frozen, and inaccessible to human use. That's about 68% here of, I don't know if this works, yep, of fresh water is frozen. Of what remains, the vast majority is groundwater. And yet, we spend most of our time thinking about regulating, managing, studying just this teeny percentage of fresh water on Earth stored in lakes and rivers. So what I'm really interested in is understanding the role that groundwater plays in our Earth system, both from a hydrologic perspective and also in management terms. So we use groundwater in a number of different ways. The town where I live in Pullman, Washington, it's our sole source of municipal water. The majority of groundwater is used as all water for irrigation in agricultural systems, and we especially see this in times of drought. This is a time series of cumulative groundwater storage loss in the Central Valley of California, starting in the early 1960s and going a little shy of present day. The tan bars are generally drier periods, and the bluer bars are generally wetter periods. So what we see is during those dry periods, we rely on groundwater more than we usually do. So we see these steeper declines of groundwater loss. But then in the wet periods, we see some rebound, but overall there's a long-term decline in total groundwater storage. Those wet periods don't bring us back up to where we need to be to maintain aquifer sustainability or equilibrium. Of course, as we've heard today, this is only going to get worse. On the right, we have figures showing projected changes in snow water equivalent. At the top, in the middle, we have runoff, and at the bottom, we have soil moisture. And the important thing here is that it's almost all red in the American West. So traditionally, as the previous figure showed, during drought periods, we like to turn to groundwater. But that's not necessarily going to be a viable strategy as we move into the future. Not only will climate change be impacting these surface supplies, but it's also going to impact groundwater. So groundwater, as we'll see in a moment, is recharged by precipitation. So in some places, we're going to have more intense precipitation with climate change. Is that a good thing or a bad thing for groundwater? It's a bad thing, because we reach a point where if the precipitation is too intense, it's just going to run off and not actually recharge our systems. In other words, as we move into a potentially drier future in the American West, we're really going to have to rethink the role of groundwater in mitigating drought in the areas where we have surface water supplies, and also in the areas where that's the sole water supply source for communities. I'm a scientist. I think we have an obligation to wear a few different hats in a changing climate, and if it weren't changing. We have basic fundamental questions that we still need answers to, and this is so true with groundwater. The number that I showed before, that about 30% of fresh water stored in the world is stored as groundwater, that number was actually developed in the 1960s. And a scientist said that there's consistent groundwater across all the continents to 2,000 meters depth of all the continents with the same porosity across all of these continents. That's the number that gave us 23 million cubic kilometers of groundwater stored on the Earth, and that's the number that we keep citing when we say that 30% of fresh water is groundwater. This is a fundamental question. How much of this resource do we have and how much are we using? We still don't know the answer to that for groundwater. As we have increasingly complex and interdependent systems, we also need to start asking new questions that we never asked before. Data isn't just a hydrologic point, a stream gauge. It's also a farmer's experience. You know, Kevin showed pictures of people who became his friends, and he went to them first because of the knowledge they had stored in their brains. We have farmers who are working with groundwater and the balance between surface water and groundwater, and we need to use that information to understand the role of groundwater in the future. Ultimately, I think a large part of our job is not limited to the research realm, but it's really thinking through how we can use scientific information to support decision-making. We heard this morning about the need to modernize our water law and incorporate changes in groundwater dynamics, and I hope we can get to the point where we can do that. All right, groundwater. It's underground. Seems pretty obvious, but that makes it really tough to study. So I'm going to go through sort of a cartoon that lays out the way groundwater looks and how it moves and how we can interact with it so that we're all on the same page and moving forward with advancing ways to understand groundwater. This is what we see, the surface. This is also what the majority of satellites can see. So this is about 24 of the 28 or so current satellite missions that NASA is involved with. There are also a lot more satellites that are orbiting the Earth, looking at different types of information. All of these are looking at some aspect of the land surface or above, up into the atmosphere. When we start looking beneath the ground, this is an example of some of the information we can get from satellite observations. These are pictures of Lake Mead from the Landsat satellite in 1984 on the left and 2016 on the right. I think one of the most interesting things about satellites is pretty obvious. They're just showing us what's happening on Earth. So the changes that we see between these 2 years, which hopefully you can see, they're not only natural changes and they're not only human-induced changes, but it's some combination of the two. When we start looking at integrated climate systems, we start off by looking at the equations, our natural governing laws of physical systems. And those natural laws don't necessarily have the human system involved. And it's up to us to develop the tools to incorporate human dynamics into our tools that we already have. And I think satellites are one way that we can start doing that, where they show us this picture and we know that we need to get there. When you start looking beneath the ground surface now, for real this time, we had one more satellite, SMAP. This was just launched, I think, in 2015, and it measures soil moisture in just the top couple of centimeters globally. That seems like a little bit, but that extra information can really help us parameterize our land surface models, so basically set us a goal of what we want our simulations to look like. When you get deeper into groundwater, we get my personal favorite satellite, the one that I spend most of my time thinking about, GRACE, and I'll talk about that in a little bit. So this is showing us an unconfined aquifer here, but none of these satellites can tell us whether it's a deep, unconfined aquifer, or maybe it's a little bit shallower, or maybe it's a little bit more complex. So here we have confining layers. These might be made of clay, where it's really hard for water to pass through these confining layers. That means that if you are looking at different management options, it's really different if you're managing an aquifer that looks like this versus this, and I'll get into why. So let's think about a natural mass balance. What should a groundwater system look like unperturbed over a long period of time? In any mass balance, in minus out equals your change in storage. So if we want natural equilibrium, we want that to equal 0. So how does that look for groundwater? Groundwater can be recharged, so the in from surface water bodies or from precipitation. I don't know if you guys can see that very well. And when a raindrop hits the land surface, it can either run off or it can actually infiltrate down into the groundwater and ultimately recharge it. As I said before, when precipitation becomes more intense with projected changes in climate, the ability of those raindrops to enter the soil might be diminished, and we'll have more running off at the land surface and less entering the groundwater system. To balance out these ins, we also turn off the screen. We also have outs. So we call this base flow or discharge. And so this is where we have our surface water, groundwater connections. In the summertime, it hasn't rained a lot, but there's still water in the river. How does that happen? That's groundwater flowing into the river. So in a natural system over a long period of time, these ins and outs balance each other, and we're happy. So recharge in minus discharge or base flow out equals your change in storage, and that's 0. But of course, groundwater is quite perturbed, more so in some places, especially the American West, than elsewhere. So now we have pumping, we're extracting a volume, and the aquifer is actually going to try to balance out what you're taking from it to maintain equilibrium. And this was put forth in a paper in 1940 by Tice. So if you are pumping close to a surface water body, you're creating extra pore space when you take water out, and you can actually pull in extra recharge. And that can have negative impacts by decreasing the surface water that you're drawing from. So in groundwater-dependent systems, let's say wetlands, if you're increasing recharge to the subsurface, then you're actually decreasing the water that you have at the land surface. One of the most common things is that you actually decrease the amount of water going out to the rivers. Again, this is the surface water-groundwater interaction. We just had an important ruling in Washington State called the Hearst decision in 2016. We have groundwater exempt wells for residential use. So I think if your land is on a half-acre plot for residential use only, then you can have a well that is exempt from other environmental regulations. And this decision basically said that those wells are still impacting the surface water bodies and that they can't be exempt from environmental regulations. So right now there's sort of a hold on new permit exempt wells for residential growth in the state of Washington because of the interaction between surface water and groundwater. Okay, so I don't have many equations, but here is one. So now we have more in and less out to maintain an equilibrium, an aquifer in equilibrium. And what we're saying basically is that we already know that recharge minus discharge naturally equals 0. So now the extra in minus the less out is ideally going to equal what we call safe yield. So when you talk about managing groundwater to be sustainable or to be a safe yield, this is what we're talking about. When you see aquifers that have actually lost storage, you're pumping more than the aquifer can replenish itself. You've passed that safe yield limit. So storage loss occurs when withdrawals exceed the aquifer's ability to balance the amount of extraction. And we want to know when, where, and why this happens so we can improve management towards safe yield. So how can we measure groundwater systems to see if we're in equilibrium or not? These are locations of wells from USGS. These are monitoring wells. And each of these points has at least one observation in an entire year for the past 20 years. These wells have one observation per month, and these wells have one observation per day. Historically, when we use groundwater locally and manage it, hopefully locally, then it's okay if we don't have that many monitoring wells, if you're in a small community. But obviously, these systems are large integrated groundwater bodies, and we have to be able to measure and understand the resource between these observation points. I learned a fun fact putting this talk together. Elinor Ostrom, her first entree into common pool resources was actually looking at groundwater in Southern California. Her graduate work was looking at saltwater intrusion into a groundwater basin in LA. And she and others say that in order to manage common pool resources such as groundwater, we need limits and understanding of how much resource you have available in the first place, what your stock is, and what the fluxes are. What are those ins and outs? And without that information, it's really tough to effectively manage common pool resources. So when you put these two maps next to each other, so on the left we have our daily well observations, and on the right we have the 40 or so aquifer systems in the US. There's a lot of data gaps in our point measurements of groundwater. This means that when we're looking at establishing aquifer level sustainability targets, as California recently did, finally on board, it's tough to figure out how to interpolate the sparse information that we have available to us. So maybe it's not that you can't manage what you can't measure, but it makes it a lot harder to manage effectively if you don't understand the resource that you're managing around. Thankfully, recent advances in airborne observations have really moved us toward being able to understand groundwater dynamics over larger spatial scales. I'm going to spend most of my time remaining time, talking about the GRACE satellites here, but I'll also talk about a technique using InSAR. This is the ENVISAT satellite in the upper right, which is a European Space Agency satellite. And then a new technology that I just learned about in December, where they're actually flying a multi-sensor array from a helicopter to map the subsurface. So let's talk about GRACE. GRACE stands for the Gravity, Recovery, and Climate Experiment. Most satellite systems are a single satellite that maybe take pictures of what's happening on Earth. GRACE is unique in that it's two satellites orbiting the Earth as a pair. And can you raise your hand if you've heard of the GRACE satellite, if you're familiar with it? All right. So each of the GRACE satellites are about the size of a minivan, and they orbit the Earth at about 400 kilometers altitude, and the distance between them is around 250 kilometers. And what they're actually measuring is changes in gravity on Earth. So before GRACE was launched, our understanding of gravitational anomalies on Earth is shown in the left-hand figure here. And then on the right, we see how the resolution tightens up. We have a better understanding of gravity anomalies on Earth because of GRACE. And a few smart people thought, what's really heavy that moves between months that could impact Earth's gravity? Water. So the way we use GRACE to look at water systems is as follows. Well, first I'll say, here's the 2 GRACE satellites flying around. And let's say they come up on a mountain range, and we know that mountain has a lot of mass. And so that mass is actually exerting a gravitational pull on the front satellite that has yet to be detected by the second satellite. So the distance between those satellites is changing as the front one is pulled down towards the mountain. Now the next month, it has snowed a lot. Now there's more mass on that same mountain range than there had been before, so there's a stronger gravitational pull in this second month. What GRACE is measuring is the difference between those 2 months as a function of changes in the amount of, in this example, snow stored on land. So GRACE is measuring the change between months in total water storage on land as the combination of changes in snow, surface water, soil moisture, and groundwater. So GRACE is seeing changes in all of the water stored on land. So you can think about GRACE data based on a water balance equation where you have your ins and your outs. And what we're interested in as hydrologists is figuring out how to play around with the total storage change that GRACE sees, that delta S, and coming up with other ways to represent the remaining components of these equations if you're interested in just one piece of it. So GRACE was launched in 2002, which means we have a little over a decade of data now to play around with. This is monthly data, so how is water stored on land changing between months? One limitation of GRACE is the spatial resolution is really coarse, so GRACE can see changes in total water storage in areas larger than 150,000 square kilometers. So let's say the San Joaquin River Basin and the Sacramento River Basin together, or the whole High Plains Aquifer, or the Amazon Basin. And again, the changes that GRACE sees are a combination of human-caused changes and natural changes. So groundwater depletion increasing because of drought. GRACE is sensing all of those changes, and we'll look at the data and see what it actually looks like. Can you hit the first video, please? This is a time series of the total water storage changes in California and the West from the start of the GRACE record through present day. So where the map is going blue, there's extra water mass being added compared to normal, and where it goes red, we're losing water mass compared to normal. Did anybody see the drought that California just had? So to me, one of the greatest benefits of GRACE is we know during drought we use groundwater more. And we know that there are floods happening in different places. And GRACE really lets us visualize that information. We see hot spots where it gets red, there's something happening. There's some sort of water storage loss that's occurring. And it's up to us to really figure out what is driving that change. The way that we have used GRACE data to look at groundwater storage changes specifically is by making a bunch of squiggly lines. So on the upper left little plot, we have a time series of California. This is the total terrestrial water storage changes in California. I think this goes to 2010. So that's the delta S in the equation. And then we come up with other estimates of snow and surface water and soil moisture, and we subtract that information out from the total GRACE signal, and what we're left with is changes in groundwater storage over the GRACE record. And in the Central Valley, this is basically showing us that where we have declines in groundwater storage, we're pumping out more than the safe yield. And we can actually quantify that by combining GRACE data with other estimates of changes in recharge and discharge, if that information is available, to know how much we're surpassing the ability of the aquifer to maintain itself in equilibrium. One great thing about remote sensing is that it's global. So we've been able to apply this technique to studies globally. This is from my PhD dissertation, looking at global groundwater stress. So I used the technique from the previous slide to look at how groundwater storage is changing in the world's 37 largest aquifers. I am terrible with this thing. I'll put it down for now. So we see reds where there's groundwater storage loss, and we see blues where there's groundwater storage gains. And this GRACE data has really allowed us to look at a global scale for the first time to be able to compare aquifers with the same type of information. You'll notice to the keen eyes in there that the High Plains aquifer is actually blue here. And that has caused some controversy. And the important thing is that GRACE data is only from 2003 to present. Where we don't have information, GRACE fills in the gaps. But where we do have more information, we can begin looking within these aquifer systems and seeing what is driving changes. In the High Plains over this time period, the northern half of the aquifer system is increasing in storage and the southern half is decreasing. And when we're looking at basin averages like this, the trend is basically around 0. So GRACE alone can't tell us what's happening within the aquifer systems. That requires additional information, but it does show us where we have hotspots to point to and basically tell us that we need to look into these systems more. One thing I'll note is if you look, it's kind of hard to see, the Ganga Brahmaputra aquifer up here has the highest rate of GRACE-based groundwater depletion of any of these aquifers. However, I could not find one single estimate of how much groundwater is actually stored in that aquifer. And that's the case with about a third of these aquifers. There aren't storage estimates. So we're depleting this resource without knowing how much is there in the first place or when we might run out. One challenge with this method is that any error in the additional components that you're using to isolate out groundwater, any errors in how you measure snow or how you measure surface water or how you measure soil moisture become propagated into the error of your groundwater measurement. So in many places, we have to rely on models to tell us how soil moisture is changing, because this figure on the right has little red dots of where we have soil moisture sensors, and just like our image of the wells, they're spread out. We don't have a great network of integrated soil moisture observations. This is again where remote sensing can hopefully play a role, especially in areas where we don't have additional data. So can you play this video, please? This is just the snow bottom left. So this is remote sensing observed snow cover from MODIS. And this is just an example of how remote sensing is adding additional tools in our toolbox to understand the Earth system. This is just snow cover, not the total volume of snow changing between these months, but it's at least a start to get additional estimates of where we have changes in these other storage components. This is an image of where we have altimetry data in the world's largest lakes and rivers. So there's satellites that can actually measure water storage or water level changes in large surface water bodies, and we can use that to estimate surface water changes. And again, we have a new satellite to measure soil moisture changes. Now, a lot of this isn't necessarily specific to the American West in the context of this symposium, but as we saw before, even in the West, we have disparate points of in situ measurements of all of these water storage components, and remote sensing can help integrate those. And in the West, we know a lot, and we can use that information to test some of these tools so we can then apply them elsewhere globally where there's less information. Now I'll just talk a little bit about other airborne observation platforms that we can use to understand groundwater storage change, and this is one that's been used a lot in California and Colorado, and I think in Arizona. So the type of soil matters in your groundwater system. If you have clay, Clay particles are kind of like plates. And when there's water between these plates, they can stay expanded in a nice matrix like this. But if you start pumping water out, then now you just have air between these plates, and they can kind of flatten out because the weight of all the soil above them is pushing down and squeezing out that air, and now you have compaction. And this figure is showing that the actual land surface compacts, which we call subsidence, if you pump out too much water without recharging it, and you have a long enough period of time where the soil actually compacts down. And this is measured with interferometric, which I always have a hard time saying, synthetic aperture radar. This is a classic example of showing subsidence in the Central Valley. This is a USGS scientist. In 1925, the ground surface was up here. This is a telephone pole. Due to large amounts of groundwater pumping and that compaction, subsidence, the land surface has actually fallen to, this is in 1977, about 30 feet of change. So this satellite system is actually able to measure that change, and we can look at what that data looks like. And this is showing, I think, yep, in inches, how much land surface deformation has occurred in parts of the Central Valley due to groundwater pumping. The final one, we're going to go back to this little cartoon. And I said before that we don't really have ways to understand what the subsurface looks like without drilling a lot. This is a new technology called SkyTEM, and the TEM part stands for transient electromagnetic. So it's an electromagnetic sensor that maps resistivity in the subsurface. And this flies from a helicopter. You can do about 1,000 kilometers, I believe, in a day, and then develop relationships between resistivity and soil properties. So you can actually map different soil layers in the subsurface to about 350 meters. I think this is one of the coolest things that I've learned about. And if it weren't so expensive, I would love to use it in Washington. We have a long history of using Earth-observing satellites to learn, to advance research, and also to help engage society with our Earth system. So on the bottom left, this is an image of satellite precipitation showing an atmospheric river hitting California. So because of satellites, we've been able to understand how these extreme precipitation events form and hit the coast of California. In the upper right, this is something you can go online to NOAA's website, and you can actually look at the precipitation in your area in the last week. You can play around with looking at weekly data or monthly data, and you can see right where you are. We have this ability for these satellites that have already been up for a while to really interact with this information. We're starting to get there with some of the GRACE data. This is the US Drought Monitor, which directly assimilates GRACE data into their projections of drought, and this is updated weekly, but we're still not at the point where you can say, I want to drill a well here, how would that impact my neighbors? But I think we're really close to being able to bring together different types of information and tools to actually get there. In order to make that happen, we need to figure out how to cross scales, spatial scales, different types of information. How do we go from an individual well to GRACE observations? How can that information be used in a groundwater flow model to project different management scenarios? These are all things we're kind of playing with now and trying to get a handle on for groundwater. And we're closer than we have been, but we're definitely not there yet. And I think really the future and what's exciting about a symposium like this is that these tools that we have don't exist in isolation in academia. The future is really incorporating scientific research with management needs, with sitting in the farmer's seat and understanding decisions that they have to make. In Washington now, we're starting to look at groundwater as a long-term drought mitigation strategy. Normally people think Washington's fine, we have the Columbia River, but groundwater is actually used for about 20% of irrigation today, and that might increase into the future. So I think with things like cloud computing, we're getting to the point where we can integrate not just scientific data points, but also experiences into decision support platforms for groundwater. But that takes a lot of communication, and hopefully that's underway. So with that, I will stop.